Hello everyone, today we are discussing the potential due to an electric dipole at any random point. So we have selected a random point, point P, which is at a distance r from the center of the dipole, and please analyze this diagram. Point A where minus q is placed, point B where the positive charge is there, and the distance of the point P from A it is r1, for B it is r2, and from the center it is r. The angle between the position vector of the point P, r, and the dipole, or also we say the dipole moment, and that angle is theta. Analyze this diagram. The net potential V at point P will be the sum of potential due to Q minus Q and potential due to plus Q. So V1 is equal to minus KQ by R1 and V2 is equal to KQ divided by R2. Therefore, the net potential V is equal to V1 plus V2. We are substituting the value of V1 and V2 and you will get this one, and finding the LCM, and finally you will get this equation number 1. Next is the assumption. So I need your full attention here. See here, we assume something, that is R is very greater than A. This R is very greater than A. It's 2A. 2A means the total distance between the charges. A means half of the dipole, half the distance. That means the distance from one charge to the center, it's A. So if R is very greater than A, that means this distance is small with respect to this R. So this point P is at infinity. Remember, this infinity doesn't mean it is at very far from the dipole. This infinity means where with respect to this distance to A, R is very large. If it is very large, look at these distances. At present, look at this. R1, R2 and R. They are different. Means R1 is the longest one, then comes R, and finally R2 is the shortest one. But if the point P is at a very large distance, R1, R and R2 will be approximately equal. Remember, I do not say it is exactly equal. They are approximately equal. So we can assume, see this one, R1 approximately is equal to R2, which is approximately equal to R. So in this equation number 1, there is R1, R2, it's a multiplication. So R1, R2, I can approximately write it is R into R. R into R, R square. So this is equation number 2. This is you are going to substitute in equation number 1 instead of R1, R2. And now, again, look at this diagram. The angle between R and dipole moment is theta. So we are assuming the point P is very far and R1, R and R2 are almost equal. Then the angle made by all the three with the dipole moment will also be approximately equal. Not exactly equal, approximately equal. So you can consider this is also theta, it is also theta, it is also theta. Now, I have made some changes in the diagram. See this. Consider triangle ANB. It is a right angle triangle. And you know already why this is theta. Okay. See, in this triangle, this is the adjacent side. And here the hypotenuse is 2a. Okay. So in triangle A and B, cos theta is equal to adjacent side divided by hypotenuse. And then you can rearrange this. R1 minus R2 is equal to 2a cos theta. You're substituting this equation number 3, equation number 2 in equation number 1. And we remember the dipole moment equation. Q into 2a, it is the dipole moment P. You substituting the value of P also, and finally you will get the potential at point P is Kp cos theta by R square. It is clear that the potential, the net potential is inversely proportional to the square of the distance. Now the special cases. Special case number 1, that random point P, if it is along the axial line. If the point P is along the axial line of the dipole, then what will be the total potential? So if along the axial line means it can be in your left hand side or maybe in the right hand side. So for you, first of all I consider the point P here. It's the axial line, the dotted line is the axial line of the dipole, and the point P is here. It is at a distance r from the center of the dipole. Now see, the position vector is towards this side. Dipole moment direction you have already studied, it is from the negative charge to the positive charge. So both are in the same direction. So P and R, both P and R, they are parallel. Theta is 0 degree and cos 0 is positive 1. In the same way, if you consider the point P in this side, so let me consider again point P in the left hand side, and it is at a distance r from the center. Now the point P, position vector is towards in this direction, dipole moment in the opposite direction, that is P and R, they are anti-parallel. That means theta is equal to 180 degree, cos 180 minus 1. So both the possibilities are there. Hence you can conclude the potential along the axial line, anywhere on the axial line, Vx is equal to plus or minus Kp by R square. Plus or minus Kp by R square. Now the second assumption, the potential along the equatorial line. Equatorial line means, see this dotted line is the equatorial line. So you are going to consider the point P. It can be anywhere on the equatorial line, maybe on the top of the dipole or bottom of the dipole. Anywhere randomly I consider here. It's a point P. It is at a distance r from the center of the dipole. Now see what is the angle between the dipole moment and the position vector. If it is on the top of the dipole or even in the bottom of the dipole, the angle they are perpendicular. P is perpendicular to the position vector. Theta is 90 degree and cos 90 is 0. And hence you know what will happen. The net potential anywhere along the equipotential surface is 0. I hope it is very clear to you.